So in this first example, we have a code that consists of 2 letters and 3 distinct digits. How many different codes could be formed? Now over here, since it involves codes, then the order matters, because whenever you are inputting a certain code, a code of 120 would not be the same as 210. It would not open the lock. So the order matters. So since the order matters, the second thing I ask myself is repetition allowed or not. So over here, since the order matters, I can use the counting principle. So I can just open 2 spaces for the letters and 3 spaces for the digits. Now, according to the given, they said it consists of 2 letters and 3 distinct objects. So the 3 distinct digits. So the digits are different. So over here there is no repetition. Well, for the letters, there's nothing in the given that excludes repetition. So over here there is repetition of letters. So if I were to be using the counting principle in order to solve this problem, now for the letters, in the English alphabet, we have 26 different letters we can choose from. So for the first letter, I have 26 possibilities. Now, since repetition is allowed, then for the second letters, I still have 26 possibilities. Now let's just move to the digits. Now the digits in the decimal system are 0 to 9, which are a total of 10 digits. So starting from 0 to 9, that's a total of 10 digits. So since repetition is not allowed here, so for the first digit, I have all 10 possible digits. However, repetition is not allowed, so for the second digit, I can choose any of the 10 digits except the one I chose for the first digit. So I have 9 possible digits for the second one. However, for the last one, again, since repetition is not allowed, then I need to exclude from the 10 digits the 2 I have already chosen for the first 2 digits. So I would have 8 possibilities for the last one. So according to the counting principle, we end up multiplying these. So n would actually be 26 squared times 10 times 9 times 8, which would in fact be, so I have 26 squared times 10 times 9 times 8, which is 48, which is 486,720. So that's a huge number of codes we can use there, right? I copied it right. Okay, however, if instead you wanted to use the arrangements, over here for the letters, it's an arrangement or permutation with repetition. So with repetition, it's the total number of objects, which are the 26 letters of the English alphabet, raised to the power of the number of objects you're choosing. So over here, since we're choosing 2 letters out of the 26 with order and with repetition, so that's 26 squared, times, as for the letters, that's you're basically arranging 3 digits out of 10. So that would be P of 3 out of 10. So if you were to find this on your calculator, it should give you exactly the same answer as the counting principle. Okay, so in this example, we have 3 math books, 4 science books, 2 geography books, and 3 history books to be placed on a bookshelf. And the books are all different. Now, in how many ways can the books be arranged on the shelf? Now, in this first part, we're looking to arrange the books independently from the subject. Okay, so over here, since I have a total of 12 books, there are 12, right? 3 and 4 is 7, 2, 9, and 3, 12. So we have a total of 12 books, okay, that we aim to arrange on a shelf. Now, of course, here the order matters, because if I put the first math book first and the second science book second, it wouldn't be the same as starting with the science book. That would in fact be a different possibility. So since we're arranging objects here, in that case the order matters. That's one. And over here what we're actually doing is arranging all of the 12 books on the shelf. So in fact here we're not choosing a smaller number to arrange out of these 12 objects. We're just considering all of them, and without repetition, of course. So over here n would just be 12 factorial. So I could in fact place these 12 books on a shelf in 12 factorial ways, which if you're curious to know how much that is 47, no, in fact, that's 479,001,600. So there are this much possibilities. So if we look at part B, in part B they're asking for the number of ways the books could be arranged on the shelf if the books of the same subject are to be grouped together. So what we're doing in part B is that we're considering a block for math, a block for science, and a block for geography, and a block for history. So now what we need to do is arrange the books this way by keeping all books of the same subject grouped together as one block. So over here, regarding the math books, I do have 3 math books. So in this block, I have 3 math books that could actually be arranged into different possibilities for the math block. So since over here I'm arranging 3 objects out of the 3 objects, so in that case for the math blocks I can rearrange the math books in that block 3 factorial ways. Similarly for the science books, now I have 4 science books that I want to arrange, so I would in fact be arranging these 4 factorial ways. For the geography books, I have 2 geography books, so the number of ways I can place these geography books would be 2 factorial. While for the history books, I do have 3 of them, so they could be arranged in 3 factorial. However, over here, if we look at each block as one object, so we're facing 4 objects here that we aim to arrange. So these 4 blocks can be arranged in 4 factorial ways. And according to the counting principle, we do multiply these number of possibilities. So that would be 3 factorial times 4 factorial times 2 factorial times 3 factorial multiplied by the 4 factorial, which is the number of ways I could arrange the 4 main blocks. Of course, you could evaluate this on your calculator in order to determine the total number of arrangements available. Now, as a part of his cross-country training, Mark runs a 10-kilometer route 4 times a week. There are 8 different routes along which he can run. Knowing that Mark can run a different set of routes each week before his next race, how many weeks are there before his next race? Now, since over here, we're aiming to look for the number of weeks before his next race, and I do know that he can run a different set of routes each week before his next race, then in fact, over here, in order to find the number of weeks remaining before the race, I need to find how many different sets of routes I can form. So over here, if we relook at this context, does the order matter? Well, in fact, no, because the first clue about the lack of order here is the word set. And we know that whenever we're forming sets, the order of elements inside the set doesn't matter. So that's your first clue for the lack of order. However, over here, of course, in addition, since here you're forming sets of routes, for example, if I have 4 routes available, road 1, road 2, road 3, and road 4, and if I aim to choose 3 routes out of these 4, if I chose road 1, 2, and 3, and then the next week I chose road 1, 2, and 4, now that's a different set, even if it had roads 1 and 2 in common, but the set in total would be different. So over here, going back to finding the number of weeks before his race. So as we said, since he can manage to find it, to run a different set of routes each week before his race, then to determine the number of weeks remaining, we'd actually be looking to determine how many different sets of routes we can form. So over here, he has 8 different routes he can run along. So over here, the total number of routes is 8. However, he does practice or run 4 times a week. So out of these 8 different routes, he needs to choose 4 routes a week. And we've already agreed that this is done without order. So N would actually be a combination of 4 out of 8, because to complete a weekly practice, he needs to have covered 4 routes out of the 8 available routes. Okay, so over here, combination of 4 out of 8, so that's 8C4 on the calculator, which gives a 70. So in fact, he still has 70 weeks before his race. Okay, now in this example, we have a team of 4 students that needs to be selected for a math competition, and we have 8 boys and 12 girls to choose from. So again, the first question you'd ask yourself, does the order matter? Now over here, what we're doing is just selecting 4 students for a math competition. So if I chose person A before B or person B before A, it would not really matter here. I would still be leaving with the same group of 4 students for the competition. So no, the order here does not matter. So in part A, I need to determine the number of ways I can form or choose that team. So over here, since I have in total 20 students, because in problem A, we're forming the team without gender restrictions, so we have 20 students in total that I need to choose 4 from without order. So that's a combination of 4 out of 20. So that would in fact be 20 C, so that's a C4, is that 4? Yes. So that's 4,845, so it's 48, 45. So 4 students out of 20 students can be chosen by 4,845 ways. While for part B, in part B they said if the team is to include at least one girl and at least one boy, in how many ways can a team be selected? Now, if we were to look at this event says at least one girl and at least one boy. Okay, so over here, if I were to look at the opposite event of this, what's the opposite of at least one girl and at least one boy? Now, why is it that I'm referring to the opposite event? Because usually if we say at least one girl out of 12 girls, there are many possibilities to explore. At least one girl would mean exactly 1, exactly 2, exactly 3, all the way to exactly 12 girls. All of these are actually part of at least one girl. However, by looking at the opposite event, what's the opposite of at least one girl? At least one girl is the opposite of no girls. No girls, it means that all of them are boys. So the number of possibilities would be easier to work with. So basically what I could do here is find the cardinal of the opposite event and then subtract it from the total that we have found here. So going back to our event, over here I don't just have at least one girl, I have at least one girl and at least one boy. Now what's the opposite of at least one girl? At least one girl, we just said, is no girls. And what's the opposite of at least one boy? It's no boys. So, however, and we should not forget to consider the opposite of the operation. And what's the opposite of and? Now that's an or. So the opposite event of the one in the question, at least one girl and at least one boy, is no girls or no boys. Now, in how many ways can we form a team with no girls? No girls, it means that all of them are boys. It means that all 4 boys, all 4 students are chosen from these 8 boys. So that would be a combination of 4 out of 8. And no boys, it means that all of the 4 students are girls. So it means that I have chosen these 4 students out of these 12 girls only. So this is C4 out of 12. Now, when it comes to the operation, it says an or here. So over here, should I be multiplying these 2 combinations in order to determine the cardinal of the opposite event? Well, in fact, no, because when you multiply, for example here, if I multiplied these 2 combinations, I would in fact in the exercise be selecting 8 students, because these 4 combinations would actually form one possibility, one team. However, over here in this case, this combination forms one possible team and this one forms another team. So since these are different possibilities, in that case we add. So over here, by adding these 2, you would have the cardinal of the opposite event. So here, to answer our question, the number of ways we can in fact include at least one girl and at least one boy would be the total, which is 4,845, or a combination of 4 minus 20, combinations of 4 out of 20, subtracting the combination of 4 out of 8 plus combination of 4 out of 12. This way, you would, in fact, evaluating this on your calculator, you'd be finding the number of teams that would actually be formed of at least one girl and at least one boy. Okay, now in this next example, we're actually considering to form 4-digit numbers. Now, here we have the digits 0, 1, 2, 3, 4, 5, and 6, from which we need to form these 4-digit numbers. Now, if we look at part A, now, first of all, forming 4-digit numbers, does it involve order or not? Now, of course it does. As I've mentioned before, when it comes to forming numbers, not codes, numbers, now the number 12 is not the same as the number 21, so the order matters. So over here, we're basically arranging these digits. Now, how many even 4-digit numbers can be formed? Now, we're not just looking to form 4-digit numbers, we want the ones that are even. Now, in this first question, since the problem involves order, the second thing I ask myself is whether it involves repetition or not. Now, does it involve repetition? Is there repetition of digits? Now, there's nothing in the question that tells me otherwise. There's nothing in the question that tells me repetition is not allowed. So, consequently, we're forming 4-digit numbers that are even, where repetition is allowed. So in part A, we need 4-digit numbers. Now, over here, if we just look at this for a second, among the objects I'm choosing, I have the digit 0. And if I were to choose the digit 0 for the first digit, for example, if I were to form the digit 0, the number 0, 1, 2, 3. Now this is not a 4-digit number, this is a 3-digit number. So in order to have a 4-digit number, the first digit cannot be 0. So I have a restriction for 0 for the first digit. So how many possible digits do I have for each of these 4 digits? Now, since over here I have an extra condition that the numbers have to be even, whenever you have a restriction, always start from that restriction. So when is a number even? A number is even when it ends with an even digit. Now, what are the even digits in this list? 0, 2, 4, and 6. So the last digit should be 0, 2, 4, or 6. So in that case, how many possibilities do I have for the last digit? Remember, always start from your restrictions. So my restriction here is that the number has to be even. So I start with the last digit. So I have 4 possibilities for the last digit. I move on to my second restriction, which is that the first digit cannot be 0. So how many possibilities do I have here for the first digit? Now, over here, since in this question, in this part, repetition is allowed, then whatever digit I chose for the last one, I can choose it again for the first one, except the digit 0. So here I still have the possibility to choose all of the non-zero digits for the first one, even if I already chose one of them for the last digit, because repetition is allowed. So over here I do in fact have 6 possibilities for the first digit. Now let's just study the number of possibilities of the remaining 2 digits. Now for the second digit, I can choose 0 again. Okay, so now I can choose the digit 0. It's okay, the number 1023 is a 4-digit number. So over here, now I can choose 0 again in addition to all of the other digits, because repetition is allowed. So for the remaining 2 digits, I have 7 possibilities. According to the counting principle, we just multiply the number of possibilities we have here. So that will leave me with 6 times 7 times 7 times 4, which is 1176. So we can form out of these digits 1176 4-digit numbers that are even. Now for the second one, how many 4-digit numbers with distinct digits can be formed? Now let me just add the word even. Let's look for even 4-digit numbers, but this time if the digits are distinct, which means that repetition would not be allowed. So again, I have that 0 is restricted for the first one, and for the last digit they should be 0, 2, 4, or 6 in order to have even numbers. So let's just observe this for a second. Suppose that for the last digit I chose the digit 2 from this list of 4 digits. Now over here, when I come to find the number of possible digits I can choose for the first one. Now over here, since this one cannot be 0, since I have already chosen the digit 2 and I cannot choose 0 for the first one, which leaves me with 5 possibilities for the first digit. However, since 0 is in this list of possible digits for the last one, suppose I chose 0 for the last digit. So in that case, you'd notice that since I've already chosen 0 here and repetition is not allowed, in that case I would no longer have the problem of ending up with a 0 with the first digit. So in that case, the first digit would actually have 6 possibilities. So you'd notice that here, when repetition is not allowed, that the choice of the last digit, whether it's 0 or a non-zero digit, affects the choice or the number of possibilities for the first one, the one that has the restriction for 0. So in this case, what I would actually do to avoid having this conflict in the number of possible digits that can be chosen for this, in that case, what I would do is, in fact, explore both possibilities separately. It's when the last digit is 0 and when the last digit is different than 0. Of course, the first digit is always different than 0. So over here, when I have 0 to be the last digit, so this is just one possibility that I have already chosen. So in that case, since I've already chosen 0 for the last digit, there's no risk of choosing it again for the first one. So I no longer have 0 among the possibilities. So all other 6 possibilities are available for the first digit. So now for the second digit, since I already have chosen 0 and I have already chosen another one for the first digit, these two are no longer available for the second one because repetition is not allowed. In that case, I would have 5 possibilities left for the second digit. Similarly, for the third digit, since I have already chosen 3 digits, in that case, I would have 4 possibilities left or available for the third digit. So over here, this one, according to the counting principle, is 6 times 4, 6 times 5 times 4, of course, times 1 as for the last one, which would in fact give you 120 possibilities. Now, however, if the last digit is even but different than 0, so over here the number of possibilities are 3 for the last one, because I can only choose now 2, 4, and 6. So 3 possibilities for the first one, for the last one. As for the first one, since repetition is not allowed, I cannot choose the one I chose for the last digit, in addition to not being able to choose 0. So that would be 5 possibilities left for the first digit. Now for the second digit, I cannot choose the one I have chosen for the last one and for the first one, but in fact I can now choose 0. 0 is now available. So that would roll out 2 possibilities out of all the 7 objects I have. So that would in fact leave me with 5 possibilities. Now out of all the 7 objects, I have 3 that are not available because repetition is not allowed. So in that case, I would have 4 possibilities allowed for the third one. So according to the counting principle, this second case had in fact 5 times 5 times 4 and times 3. So that's in fact 300. So I could either have these 120 numbers or these 300 numbers. So that's in fact an or. They are different possibilities. So in that case, the total number of even 4-digit numbers with distinct digits I can form is in fact the sum of n1 and n2. So that would in fact be 420 total numbers. Now in this next example, we are given a deck of playing cards, of 32 playing cards, where a hand consists of 4 cards. Well, you know, usually a complete deck of cards consists of 52 cards. So over here, we actually have 32 playing cards. Whenever they say a deck of 32, a deck of 32 would actually consist of, they always do, they consist of the cards from 7 to 10, in addition to the Jake, to the Queen, to the King, and to the Ace. From 7 to the Ace, that's a total of 8 cards, and with 4 suits, that's 8 times 4, which is 32. So whenever you see a deck of 32 cards, it's always these set of cards for each suit. It's starting from 7. So 7, 8, 9, 10, then the Jake, Queen, King, and Ace. Okay, so out of this deck of 32 cards, a hand consists of 4 cards. So we're selecting 4 cards out of the 32 cards to form a hand. So the first thing you need to ask yourself here, before we actually look at the question, does the order matter? Well, in fact, no, because whenever you select cards in a card game, whenever you're playing cards, the order in which you actually hold the cards would not really matter. You could just hold them in any order you want. The hand would not really change. So for that reason here, order does not matter, and when the order doesn't matter, that's combinations. So how many total hands can be formed? So the total hands that can be formed when you're selecting 4 cards out of 32, so that's a combination of 4 out of 32. Now you'd notice here that 32C4, now that's a really huge number, so that's 35,960. So I can form 35,960 hands of 4 cards. Now, how many hands consist of 4 cards of the same color? Now, we know that playing cards are divided into 2 colors, black and red. So in that case, 4 cards of the same color. If in total I have 32 playing cards, then these 32 playing cards have 16 black cards and 16 red cards. So I want 4 cards of the same color. So 4 cards of the same color would usually consist of all 4 being black, whatever the suit is, all 4 being black, or all 4 being red. So in that case, my hand of 4 cards has to be chosen from the 16 black cards or 4 cards out of the 16 red cards. So it's 4 out of 16 black, or, so that's a sum, 4 out of the 16 red. So you'd actually evaluate this on your calculator. That would be 16 C4, and that's a times 2, so that's 3,640. Okay, now how many hands consist of 4 cards of the same suit? Now we know that a deck of cards contain 4 suits, which are the diamonds, the hearts, the spades, and the clubs. So 4 suits with a total of 32, it means that 4 suits with 8 cards each. So I have 8 cards, 8 hearts, 8 clubs, 8 spades, and 8 diamonds. So over here, for each one, for example, if they were to be 4 hearts, in that case, it would be a combination of 4 out of the 8 hearts. Similarly, it's an or 4 clubs, so that's a combination of 4 out of the 8 clubs. Similarly, for the 4 suits, I would be adding this combination to itself 4 times, so that would be 4 times this combination. So it's 8C4, and of course times 4, which is 280. So we actually have 280 hands that consist of the same suit. Now, how many hands contain exactly 1 ace? We know that out of the 32 cards, I have 4 aces. So out of the 32, I have 4 aces, and the remaining ones, which are 28, that are not aces. So if I want my hand to contain exactly 1 ace, that would in fact be equivalent to choosing 1 card out of the 4 aces and the remaining 3 cards out of the remaining 28 aces, 28 cards. Now you'd notice that the number of selections here, 3 and 4, they form the total number of cards in the hand, while the number of totals here, 28 and 4, together they form the total number of objects we started with in the first place. So I will repeat, to contain exactly 1 ace, so I need 1 card out of these 4 and 3 cards out of these remaining 28 cards. And since over here, this 1 card and this 3 card, they form together 1 hand, in that case you'd multiply. Okay, but since they don't form different hands to add, it's the same hand, so in that case we multiply. Okay, so over here that's 28C3, and that's a times 4, combination of 1 out of 4 is a 4, so that's 13,104. Okay, now similarly, in how many hands contain exactly 1 heart? Now we know that we have 8 hearts, so I need to choose to have exactly 1 card that is a heart. So it's 1 out of the 8 hearts times the remaining 3 cards out of the remaining 24 cards that are not hearts. So in this case, that's 24C8, 24C3, sorry, times 8, because C1 out of 8 is 8, so that would be 16, 19, 2. So it's 16,192. As for the last question, they're asking for the number of hands that contain exactly one ace or exactly one heart. Now, does it mean that, since it's an or, does it mean that it's the sum of the answer in part D and the answer in part E? So is it 13,104 plus 16,192? Actually, no, because over here, whenever you say or, you do add them when they do not have anything in common. But however, one ace and one heart do have a card in common, which is the ace of hearts. So in fact, if I have a hand that contains the ace of heart only, the only card that is an ace or a heart, in that case it would fall under this event. So usually whenever we say A or B, whenever we say A or B, that would in fact be equivalent to A only, B only, or A and B together, their intersection. Okay, so A or B is equivalent to having A only, B only, or A and B together, the intersection part. So over here, exactly one ace or exactly one heart is equivalent to having exactly one ace that is not a heart, or exactly one heart that is not an ace, or the ace of heart. Okay, so over here, exactly one ace that is not the ace of hearts. So we know that there are 4 aces, okay, which I have 3 aces that are not a heart and 1 ace that is a heart, right? And then for the remaining cards, we have 28 cards that are not aces, right? So over here, to have exactly one ace that is not a heart, in that case the hand of 4 cards should obtain or should include one ace out of these 3 aces. So it should be an ace that is not a heart at all. So over here, that would be a combination of 1 out of 3. Now, for the remaining 3 cards, the remaining 3 cards should not be aces, and at the same time, they should not be a heart. Okay, because I want exactly one ace with no hearts in this hand. So over here, the 28 remaining cards, in fact, have 7 hearts in them, because the 8th heart is the ace, which we already rolled out of the 28. So over here, the 3 remaining cards should be out of the 21 cards that are not aces and are not hearts. Then, or, it's a plus. Over here, similarly to how we did the first one, exactly one heart that is not an ace, and we should not have any aces in that hand. So over here, exactly one heart. We know that we have 7 hearts, out of which 6 are not aces, okay, and 1 of them is an ace. So for the card that is a heart and that is not an ace, that one card should be chosen out of these. Sorry, we have 8 hearts, so this is a 7 here. So this one card should be chosen out of the 7 hearts that are not aces. Now, if we look for the remaining 3 cards, the remaining 3 cards should not be aces or hearts at all. So for the remaining 3 cards, these 8 cards are out of selection, and for the remaining 24 cards, we should not forget that among these we have 3 aces that we don't want to choose. So removing these 3 aces, we'd still have a total of 21 to choose from. Okay, well, for the last one, I need the ace of heart as the only card that has a heart and an ace. So that's 1 out of 1, because I only have 1 ace that is a heart in a deck of cards. While for the remaining 3 cards, let's just determine their total. Their total should not have any aces or hearts. We know that in total we have 4 aces and 8 hearts with 1 card in common. So that's in total of 11 cards if we were to count the card in common ones. So these 3 should be selected out of 11. So evaluating this on your calculator would actually give you the number of hands that contain exactly 1 ace or exactly 1 heart.